Welcome to all the physiotherapy students and practicing clinicians joining us. This is a focused academic review of the foundational principles of electrotherapy. Our goal here is to build a really solid, clinically relevant understanding of the currents that form the basis of our practice. So let's begin.
Here is our roadmap. We're going to start with the fundamental physics of current, making that crucial distinction between direct and alternating types. From there, we'll dive into how these are modified for therapeutic use, looking at galvanic, faradic, sinusoidal, and diadynamic currents. And we'll wrap it all up with a clinical synthesis to tie everything together for your practice and, of course, for your exams.
Before we can apply any electrotherapeutic modality effectively, or, just as importantly, safely, we absolutely must have a precise understanding of the current's fundamental properties. This classification really is the bedrock upon which all our treatment parameters and physiological effects are built.
Okay, let's move into our first major classification, direct current. And the single most important concept to grasp right here is its defining characteristic, a constant unidirectional flow. Honestly, this one fact is the key to everything that follows.
So, by definition, direct current, which you'll also hear called galvanic current in the clinic, is a continuous and unidirectional flow of charge. It's this unwavering one-way street directionality that allows for the accumulation of charged particles under the electrodes, and that leads directly to its very distinct physiological impact, which is primarily chemical in nature. This waveform visualizes that defining characteristic perfectly. Just look at how it remains entirely on one side of that isoelectric or zero line. This represents a constant polarity. It never reverses. And this sustained polarity is exactly what drives the accumulation of ions and results in those significant chemical effects we see under the electrodes. So the crucial point here is that DC's effects are overwhelmingly electrochemical, or what we call polar effects. We literally see changes in tissue pH and even electrolysis happening right at the skin. This powerful chemical mechanism is precisely what we harness for iontophoresis, using that current to drive charged drug ions right into the tissue. Now, if we interrupt the current, it can produce a tonic stimulation, but its primary identity is, without a doubt, chemical. Now let's contrast that sharply with our second fundamental type, alternating current. If DC is defined by its one-way flow, AC is defined by its continuous bidirectional flow. And this is the basis for its primarily excitatory effects on nerve and muscle. The formal definition tells us that AC is a continuous bidirectional flow that periodically reverses its polarity. This reversal is cyclical, and in its purest form, it's symmetrical. This cyclical back and forth is the whole reason its physiological effects are fundamentally different from DC. And this slide shows that polarity reversal in action. See how the waveform smoothly oscillates, spending equal time and having equal amplitude on both sides of that isoelectric line? Physiologically, this symmetrical flow means the net chemical effect is zero. Why? Because the effects of one phase are completely canceled out by the subsequent opposite phase. So, with minimal to no net chemical effects, AC's therapeutic value lies in its amazing ability to stimulate excitable tissues. We're talking nerves and muscles. The frequency of the current then becomes a critical parameter, allowing us to preferentially target either sensory or motor fibers. This principle is absolutely foundational to some of our most used medium-frequency currents, like interferential and Russian stimulation. Okay, let's synthesize this because it's so important. DC is unidirectional, which results in significant polar effects, making its primary mechanism chemical. AC is bidirectional, resulting in minimal polar effects, making its primary mechanism excitatory. Getting this distinction clear is absolutely critical for all of your clinical decision-making. Right, so building on those fundamentals, we'll now look at how direct current is modified for specific therapeutic applications. We're going to focus on galvanic and faradic currents. First up, galvanic current. And let's be really precise here. Galvanic current isn't truly a modification, but it's the clinical term we use for the application of continuous direct current. So when you read galvanic on a machine or in a textbook, just think DC applied therapeutically. Its use is almost entirely centered on leveraging those powerful polar effects, with iontophoresis being the classic example. Now, faradic current is designed for something completely different, excitation. Specifically, its job is to produce a tetanic contraction for innervated muscle reeducation. It's really important to distinguish the historical faradic coil, which actually produced an asymmetrical AC, from what we call faradic type currents today. These modern versions are typically pulsed waveforms, either interrupted DC or biphasic, and they're engineered to efficiently stimulate motor nerves without the unwanted polar effects of continuous DC.
In the same way we modify DC, we also modulate alternating current. So here, we'll examine sinusoidal and diadynamic currents. Both of them are derived from an AC source, but they're adapted for very different clinical goals.
Sinusoidal current is essentially a pure, low-frequency AC, often right at 50 Hz. Because of its excitatory nature and its ability to cover a large area, it was historically surged, meaning it was ramped up and down, to produce rhythmic contractions in big muscle groups. Now, diadynamic currents are a fascinating family of waveforms. They all originate from a single source, a 50 Hz sinusoidal AC. This AC is then rectified, a process that basically converts the bidirectional AC into a unidirectional pulsed current, and that forms the basis for all the various diadynamic modes you'll use. Let's break down this table of the primary diadynamic modes. First, we have monophase, fixed, or MF. This uses full wave rectification of that 50 Hz source, which results in a 100 Hz pulsed current that we use for strong sensory stimulation and analgesia. Second, diphase fixed, or DF, uses half-wave rectification, giving us a 50 Hz pulsed current. This is less intense and is often used for initial pain modulation. Then you get the combinations. LP alternates between MF and DF to achieve longer-lasting analgesia, while CP rapidly alternates them to produce a very strong counter-irritation effect. Okay, let's bring all these concepts home. This final section is all about a comparative summary designed to consolidate this information for really effective clinical reasoning and, of course, for exam review. This table is really your high-yield summary, directly comparing each current. So look at galvanic. It's from DC, its key effect is electrochemical, so its primary indication is iontophoresis. Makes sense. Then ferratic type, it's a pulsed waveform, its effect is excitatory, so we use it for innervated muscle re-education. Sinusoidal is pure AC, also excitatory, for large area stimulation. And finally, diadynamic currents, modified from AC, focus on sensory modulation for analgesia. Grasping these direct links between the parent type, the effect, and the indication is absolutely essential. And to wrap up, here's a question for you to consider. Based on everything we've reviewed and thinking specifically about the physiological principles of nerve accommodation, why is a rapidly changing pulsed waveform like a Faraday-type current so much more efficient at getting a motor response than a steady, continuous galvanic current? Reflecting on this will really solidify your understanding of these foundational principles.